The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. This is Kevin Humanick. Welcome to this month's SLCan webinar. Today we have Dr. Dave Phillips from Thermo Fisher Scientific. Dave will be presenting his topic, Biological Safety Cabinets, Selection to Installation to Operation. And we're very happy to have Dave present today. I'll introduce Dave in a little bit more detail in one moment. Just wanted to make sure that those people who are attending are aware that you can submit questions for Dave as he presents by going down to the question dialog box on your menu screen and submit your questions in writing. At the end of Dave's presentation, I'll relay your questions to him and he can give an answer to you, or you can contact him offline for more detailed questions. So without further ado, Dave is a representative from Thermo Fisher Scientific. He has been involved with biological safety cabinets for over 35 years. He worked with a nationwide BSc certification and service company in a variety of roles, including technician, regional, and general manager and technical support. He was an instructor with the Harvard course on biological safety cabinet certification. He served as an instructor with the Eagleson Institute and has organized and taught courses for the Controlled Environment Testing Association and the annual conference of the American Biological Safety Association. He's on the NSF Joint Committee for NSF ANSI 49 and has been an NSF accredited BSc field certifier under the enhanced program for over 25 years. He has a doctorate in management from the University of Maryland, and since 2007, Dr. Phillips has worked with the BSc product management team at Thermo Fisher Scientific with the responsibility for Thermo Scientific BScs worldwide. One of Dr. Phillips' key areas of interest is in improving BSc sustainability globally. So thank you, Dave, for being here with us today. And without further ado, please take it away.
Okay, thanks, Kevin, and thank you, everyone. Basically, I'm a biosafety cabinet person. I'm one of those people that are fortunate to have their hobby be their job. I just find them very interesting pieces of equipment. There's so many different factors that go into how they're used and who's involved. I mean, regulators and safety people and architects, and it's a very kind of, for me, it's a very complex and interesting environment, and I appreciate the opportunity to speak with you all, and even more to hear back from you and the questions and whatever emails that would follow. So today we want to talk about how to select, install, and operate Class 2 biosafety cabinets efficiently and sustainably. And then we also want to talk a little bit about some possible future directions. So let me see if I can get the slide to change. So there we go. So as we begin, let's lay some groundwork on what we are talking about. Class 2 biosafety cabinets, or BSCs, provide personal and environmental protection from biological hazards like dangerous viruses and bacteria. In addition, they provide product and cross-contamination protection for cell culture and other work within the life science laboratory. They are also used for the aseptic preparation of medicine within healthcare pharmacies and similar kind of controlled environment, clean environment preparations. And these illustrations, notice we have the arrows drawn in the front. That's the green arrows at the front opening. This inflow velocity keeps the particles and air that are inside the cabinet. And this inflow air is drawn into the front grill, travels under the work surface, and is pulled up inside the rear wall to the motor plenum above the work area. That's where you see the red arrows on the first two illustrations on the left. From there, the air is either pushed out through the exhaust filter on top, see where the arrows change from danger red to clean blue, or pushed down through the downflow filter to the work area, where it flows smoothly and uniformly until it reaches the work surface. And at the work surface, it splits with some going to the front, where it meets up with the inflow air and travels into the work surface and such, back to the filters. and the remainder of the downflow air goes to the back grill, where it meets up with the inflow and downflow air in their journey inside the back wall up into the motor plenum. Sometimes the BSC users need to work with volatile toxic chemicals with their microbiological work. Unlike viruses and bacteria, these volatile toxic chemicals are not particles and, like air, will pass through the filters. The inflow velocity at the front prevents these volatile chemicals from escaping out the front opening, kind of like a fume hood, but we still need to do something about the filtered air exhausted from the cabinet because it could contain these chemicals. 70 to 90% of Class 2 BSCs are Class 2 type A2 BSCs that are not connected to an external exhaust system, and this is shown on the far left illustration. These are biosafety cabinets that are designed to contain biological hazards, and since all biological hazards are particles, viruses and bacteria, as particles, the filters handle them easily. When working with volatile toxic chemicals, the easiest thing is just to connect the BSC to an external exhaust system, the same system we might use for the chemical fume hoods. We show this in the middle illustration. We don't want the exhaust connection to disturb the BSC air balance by pulling too much or allowing too little, so they're required to be connected using a canopy or thimble connection. This type of connection has a gap at the point of connection that draws in air from the laboratory and acts as a sort of shock absorber. You can see on the middle cabinet the green arrows at the top being drawn into the thimble. If the building exhaust fluctuates, the variation affects the inflow at that gap, but not at the BSC, not at the front of the BSC. Typically about 30% of the BSC exhaust volume is drawn in through the gap. So if the BSC is exhausting 250 CFM, the thimble will draw 325 CFM, 250 of that from the cabinet and 75 from the room. Most externally exhausted BSCs are canopy connected A2s. And that 30% is something that can be adjusted depending on the design of the particular canopy you're looking at. And we'll be talking about that a little later, how to pick maybe the proper amount of that extra to pull in. Now, there are some applications where there is a desire for no recirculation of volatile chemicals within the cabinet. And the most common example of this is work with hazardous drugs in the pharmacy. For these applications, they will sometimes choose a Class 2 type B2 BSC illustrated on the right. This cabinet must be connected to an external exhaust system, while the A2s that we've been looking at before push air out of the cabinet with their own internal fans, and the external exhaust just has to catch it. For a B2, there is no extra, the cabinet fans don't push the air out the exhaust at all, and it's completely reliant on that external exhaust. So it's the external exhaust that must pull the air out of the cabinet, so where we only needed a negative static pressure on the canopy connected A2 of 0.1 to 0.5 inches water gauge, we need 1.7 inches or more for the B2. Notice the airflow pattern in the BSC work area is the same for all these cabinets. The inflow comes in the front, the downflow comes down from the top and splits, with some going to the front and some going to the back. Unlike the A2, the B2 does not recirculate filtered air for the downflow, but draws it in from the laboratory at the top of the cabinet, filters it, and pushes it into the BSC work area. After the cabinet has pushed the filtered downflow air into the cabinet, the external exhaust system pulls the downflow and inflow under the work surface up inside the back wall, through the exhaust filter, and out of the building. Class 2 type B2 BSCs are the second most popular type of Class 2 BSC, but make up less than 5% of all Class 2 BSCs. And here's our first opportunity to improve sustainability and efficiency. Over the last 10 years or so, my colleagues and I have been doing BSC energy and use surveys. We will survey the laboratorians as to their use, how many hours a day is the cabinet on, do they turn it off at night, etc. We look at the cabinet itself, the energy consumption from the fan and lights. We look at whether it's connected to external exhaust. We take all of that information and calculate the annual cost of operation. Here we've taken all the information from the surveys we've done to date. We've extrapolated the energy data from makes and models we tested to makes and models we couldn't test. After filling in the energy data, we filled in the use data by randomly distributing the average types of users in proportion to their surveyed frequency. We applied an average cost of electricity of 10 cents per kilowatt hour and an average cost of $5.79 Canadian dollars per CFM per year to estimate the cost of operation for every cabinet we surveyed. This chart ranks them by cost from a low of less than $1 per year to the highest at $7,786 per year. And the first thing to note is the huge variation. The most costly units are practically consuming their purchase price every year in exhaust and energy. Secondly, I've added some detail and colored the columns red, representing Class 2 Type B2 BSCs. Remember, these are the total exhaust cabinets. The other externally exhausted cabinets, the thimbled A2s and B1s, are in gold, and the non-externally exhausted A1s and A2 units are in blue. And we can see clearly external exhaust is a huge factor in the annual operating cost. So BSCs capture viruses and bacteria. BSC users want to use chemicals that may have toxic fumes, and for that, they need externally exhausted cabinets. But externally exhausted cabinets are very costly. But from the user's perspective, a couple things are going on. First, for some users, if they're selecting a cabinet and we were to ask, are you going to work with any chemicals? We should actually say volatile chemicals, because it's the chemicals that are or become gas that pass through the filters. Anyway, they say, I'm not sure, why do you ask? And we say, because if you want to work with volatile chemicals, we should get an exhausted BSC. And sometimes they say, well, just to be safe, let's go ahead and get an exhausted BSC. They don't really want to think through all the possible chemicals and whether they're volatile or not and how bad they want to use it and all that. So they say, well, just to be safe, let's get an exhausted BSC. This is difficult, but the heart of this particular problem is that the consequences of the decision were not fully considered. We didn't say that you should know an exhausted cabinet costs, the cost of operating an exhausted cabinet is more than 3 times the cost of operating a cabinet without exhaust, and that's going to cost you an extra $2,000 per year. And we really didn't say, and oh, that $2,000 will reduce your operating budget, because for most laboratories, these costs are split up and taken up from everybody as overhead. This would be like going into Tim Hortons, and when they say, would you like coffee with your meal? You say, of course. But when the check comes at $60 and it turns out that the coffee was $50, your decision-making process classed the coffee choice as not having a significant cost, so you didn't really check your wallet. You just thought about it as if it was your preference. Similarly, some BSC users class the decision as to whether to exhaust their cabinet or not as not having a significant cost and just give their preference. In some ways, choosing an exhausted cabinet just in case is more of a decision not to decide. Let's look at something else that muddies the water. Here are the usage recommendations from the definition section and some different versions of NSF ANSI 49. We're going to look at the first 2 columns. NSF ANSI 49 is the authoritative standard for Class 2 BSC design, construction, and performance in North America. I'm just showing the A2 and B2 types as those are the most common and the contrast is the greatest. Before 2011, back to 2002 and even earlier, the usage recommendation for A2 cabinets, again, the most common type of Class 2, was type A2 cabinets used for work with minute quantities of volatile chemicals and tracer amounts of radionuclides required as an adjunct to microbiological studies must be exhausted through properly functioning canopies. Of course, we understand the thinking there as we thought through and compared the different types of Class 2 BSCs on one of our first slides, and we know what a canopy does for us. And just as a side note, this kind of reference to minute quantities is still found in the Canadian Biosafety Handbook, I think, of 2015. In contrast, the usage recommendation for B2 cabinets is type B2s may be used for work with volatile chemicals and radionuclides as required as adjuncts to microbiological studies. Almost the same, but missing the minute qualification. Our Tim Horton exhausted BSc decision prior to 2011 was even more difficult back then. If they knew or suspected they would work with volatile chemicals, they had to decide between a canopied A2 or a B2. They might be asked, do you need a canopied A2 or a B2? And quite reasonably, they would respond, what's the difference? And some, looking at these usage recommendations, would say, well, if you're going to use minute amounts of chemicals, an A2 is okay. If you use more than that, a B2 is recommended. More reasonable still, they might ask, well, what's minute? Well, no one knew. A canopied A2 would be just, I don't know for sure if the uncertain use of chemicals would be minute, so most people said, well, I guess I'm going to go with a B2. This information-weak decision-making environment, in this information-weak decision-making environment, the even more costly B2s seem to be the safest. And remember, this can have lasting effects. One of the first energy and use surveys I did, I was at a North American university, and we happened to be in this laboratory, and they happened to have B2 cabinets. And after we asked, you know, how often do you run the cabinet per day, and all of our normal questions, I said, just out of curiosity, why do you have a B2 cabinet? And they said, what are you talking about? And I said, well, this is a class 2 type B2 cabinet. It exhausts all of the downflow air, all of the inflow air, and has no internal filtered recirculation. And usually people select this type of cabinet for a particular application. And they said, well, we just moved into this laboratory 6 months ago. We don't know anything about that. So this particular university, and this ended up being the most expensive cabinets they operated on the entire facility. The user wasn't even aware of the difference, and of course, the university is getting no benefit of the different design. At any rate, in 2011, the confusing minute was eliminated, which is good. The amount of volatile chemical does not make a difference, does not escape out the front opening. A larger quantity of volatile chemical doesn't make escape out the front opening more likely. The amount of volatile chemical does not make the escape out of a canopy more likely. But as a side point, how is a class 2 BSc not a fume hood? Because some of the things we run into, and you may run into it also, laboratorians have asked, well, why do I need a fume hood and a BSc? Can't I get a BSc, perhaps a B2, and save some space? Isn't a B2 a fume hood and a BSc? Well, there are two main technical differences, of course. First, the exhaust from a BSc goes through HEPA filters, and the HEPA filter media is a fiberglass-like material, and some chemicals will adversely affect them. A fume hood, in contrast, is designed to handle many kinds of chemical fumes, including corrosive ones. Second, it's not just the filters. The fume hoods themselves are constructed out of materials designed to be chemically resistant. In contrast, BSCs are built out of materials that are easy to clean to reduce the biological contamination. So the stainless steel in a BSC may be more vulnerable to some chemicals than the typical fume hood. But the official way to respond back then was to note that the NSF usage recommendation stated may be used for work with volatile chemicals and nucleides required as adjuncts to microbiological studies. It's not a fume hood because it's only intended to handle the types and quantities of chemicals used as adjuncts to microbiological studies. Of course, another thing I should mention is that the old use of minute for chemicals in canopied A2s but not in B2s has fed into this idea that B2s are safer than A2s. So even today, we'll run into scientists that may say, well, my application is particularly hazardous or critical, and I need the extra safety of a B2. And then if you ask them what chemicals they're using, they say, well, I'm not really, it's not a chemical issue, it's just the biological agent that I'm concerned And of course, it's not really true at all. And if you factor in the increased complexity of a B2, it's more likely that the B2 is less reliable and by extension less safe than a canopied A2 or a normal A2. But one of the main things I wanted to talk about today is a change that went in 2016 on how to choose between the different types of BSC and consider about how we might be able to use this to help our clients make safer and more sustainable choices. Let's look at the column on the far right for the current recommendations. Notice that they are essentially the same for A2 and B2 cabinets and for the other types too, and say that you can work with volatile chemicals if permitted by a chemical risk assessment. Refer to Annex E, Section E313. So what's Annex E, Section E313? NSF ANSI 49's full title is NSF ANSI 49, and of course the current version is 2018, Biosafety Cabinetry, Design, Construction, Performance, and Field Certification. In addition to the main part, it includes the scope, material, design, and construction, and so on. It has 11 annexes on a variety of subjects, including Annex E, Biosafety Cabinet Selection, Installation, Use, Lifespan, and Decommissioning. And incidentally, free copies of Annex E can be downloaded from the NSF website. Section E3 is BSC class and type selection, and it is structured to go through 5 questions that need to be addressed to make the proper selection. Our usage recommendations reference question 3, what types and quantities of chemical vapors will be generated in the BSC. Remember, this section replaces all of the chemical usage guidance, including the required as an adjunct to microbiological studies qualifier that we used to use. So what do we have to fend off the BSC and fume hood people? Well, the 2 highlighted sections talk about how BSCs do not have explosion-proof components, so you should not use flammable or explosive materials in quantities above their explosive limit. The second part explains that some chemicals may destroy filter medium, so you need to avoid those. The remainder of the section notes how the effect of recirculation within the cabinet varies with the type of cabinet. Remember, there is some filtered recirculation in the type A2 and no recirculation of any kind with the B2. And then it gives 5 items that are the user's responsibility should they want to use flammable or explosive chemicals within the BSC. I suggest one way to help our laboratorians is to avoid less sustainable, less efficient BSC selection is to go through these items with them. Here are the 5 items the annex says we or the user must address. The first one is that we must be fully cognizant of the properties of the chemicals and the hazards associated with them. Before I continue, let me say that we're entering the realm of my proposed approach. I'm looking forward greatly to your comments after my presentations for any suggestions or alternatives you might have. Anyway, continuing on, the easiest way I've found to discover the properties of chemicals is through the safety data sheets. They are required by various regulations and tend to give a standardized format with the characteristics of chemicals. For our discussion, I picked an example. I had a question from someone who needed to work with isoflurane, an anesthetic gas used in this case on mice. I wrote out this table to keep track of the results. Notice this is for illustrative purposes only. If you or your clients want to use isoflurane, you need to do your own assessment based on what you'll be using, how you will be using it, and so on. For this illustration, I looked up a safety data sheet from Zoetis on isoflurane, and it said that it can cause skin and eye irritation. That's important for the user, but not for what we're trying to do, select a cabinet. Reading through the SDS, they talk about avoiding flames and sparks, so flammability is a concern. Its lower explosive limit is 14.5%. Another SDS I found said that exposure of 0.5% to 3% for 7 to 10 minutes can induce general anesthesia. I found a protocol for using isoflurane that has them releasing 800 milliliters per minute of 3% isoflurane for the mice. And so we'll use that for an example of the application for a pretend case. Now, I'm way out of my wheelhouse on this, so we definitely would want to get a chemical safety officer to work with in gathering and assessing this information on whatever chemicals they're using. But let's get back into our wheelhouse on the peak concentrations we might find in different types of Class 2 BSC. Remember, with Class 2 BSCs, you have inflow coming in the front grill, downflow coming down and splitting to the front and rear. For Type A cabinets, the downflow and inflow mix, and some is exhausted, and some is recirculated. At first, it seems tricky to factor in, say, 800 milliliters per minute of 3% isoflurane, and then some recirculates and some exhaust, and then more of the 800 milliliters per minute of 3% isoflurane is being released, and then some is recirculated and some is exhausted. At first, it's not very much, but then some recirculates and more is added. And how do we figure in all that? Well, Stewart, First, Jones, and Eagleson did a great study back in 1983 that showed that for A1 and A2 cabinets, the peak concentration of a gas being steadily released into a BSC is basically the released gas as a proportion of the inflow air. So a typical 4-foot wide A2 might have an inflow of 275 CFM. Pulling out our calculators, we can see that with the isoflurane would reach a concentration of about 3 parts per million, or 0.003% within the BSC work area. So at first it would start off low, but then as you kept on releasing the gas over time, it would reach that 3 ppm. That 0.003% is well under the 0.5 to 3% required for anesthetic effect, and the 14.5% for the explosive limit. So we filled in the 3 ppm for the peak concentration for the canopied A2. A B2 will be less. Remember, there is no recirculation on this type of cabinet, so its peak concentration in the BSC would be 0. Another factor might be the concentration in the exhaust. Continue with our example, the BSC exhaust for the canopied A2 is 3 parts per million. When it mixes with the room air coming in at the canopy, the concentration drops to 2.3 ppm in the exhaust duct. It's a little unlikely, but we might have a situation where the concentration in the exhaust duct is at or near the explosive limits, but if it was a B2 cabinet, or better yet, a wider B2 cabinet with more than twice as much exhaust air, a 50% reduction in concentration would be desirable. So as an example, if we did our isoflurane example in a 4-foot B2, the concentration in the exhaust air would go from 2.3 parts per million to 1 part per million. And yes, it's true, there might be a protocol where the explosive chemical is diluted down to just over the explosive limit in a canopied A2, but under it in a B2, but it's unlikely. Taking a step back, let's notice there's a significant difference between the canopied A2 and B2, and it's often not a significant one. Certainly not worth the additional cost of over $2,800 annually. I think we would find this almost all the time where the difference in a canopied A2 and a B2 is not significant. We would also frequently find that we may not need an exhausted cabinet. Often when you ask people what chemicals are you using, they'll list chemicals that may not even be volatile. Even with the isoflurane example, a 3 part per million release of 275 CFM into a ventilated laboratory won't reach the anesthetic levels of 0.5 to 3% in the lab. I would still recommend an exhausted cabinet in that case, but some of the other chemicals used in the BSC may not need exhausting. And the ramifications, the cumulative ramifications of these types of decisions are significant. If you have a new lab building with 50 BSCs and 25 are exhausted, that's over $7.5 million in exhaust over the life of the cabinets. So let's return to this a little later. There is some good news. Remember that most of these laboratories must be negatively pressurized and that the air drawn from the laboratory cannot be recirculated. You would know this better than I, but it certainly varies with the laboratory, size of the room and such, but most of the negatively pressurized spaces I'm familiar with seem to have at least 300 CFM being drawn from the room. But if we need to exhaust 300 CFM of air from each of our hypothetical labs, and canopied A2s can be easily integrated into ganged exhaust, and they can, and they don't require unusual negative static pressure, and they don't. That means in each lab we have one free exhausted BSC. Or, using the canopied A2 from our isoflurane example, we might have to go from 300 CFM to 360 CFM, and that 60 CFM will cost us $350 more per year, but way less than $2,000 extra. So if we have a free BSC, as we're planning our new building and asking about what types of BSCs are needed, we could include an informational pamphlet on the types of Class 2 BSCs and what are their typical uses. We would find nicer ways to say this, but we could indicate that each laboratory can have either one fume hood or one canopy connected type Class 2 type A2 BSC, and then give the uses for each. If the laboratory wanted more than that, or a Class 2 type B2 BSC, they would need to provide more information. And that information would guide us through something similar to the process we just looked at. This could make a big difference. My thought, and again, I'd like your feedback, my thought is that the free canopied A2 or fume hood would capture those casual users without costing your facility or pushing the project into some sort of universal justification process that would get a lot of people upset. They've never had to answer these questions before, and so now we might have problems. If we can winnow down the population of BSC users to the determined casual user who really doesn't want to think about it but still wants more exhaust than we're offering, and those that truly need the extra capacity, it's a much more feasible process to try to manage those through some sort of a justification process. So what else could we do? Another differentiator we found in cabinet consumption of energy was what people did when the cabinet is not in use. Most, over 2/3, turn the cabinet completely off. And that's a good thing. It consumes little or no energy, the filters are not loading, the motors are not aging in the same way, etc. There are some older recommendations that suggest that the BSC should be left on all the time. Here's an example of that recommendation from the 2nd edition of Primary Containment for Biohazards, Selection, Installation, and Use of Biosafety Cabinets by the US CDC and NIH. It appears that one of the best reasons they could come up with to leave the cabinet on the time was that it tends to clean the air in the laboratory. I would note there's no mention that leaving the BSC on would be good for the BSC sample chamber. On the other hand, every series guideline for using a BSC, including the Canadian Biosafety Handbook, has the user wiping down the interior surfaces before they start work and after they're finished, and again before they shut down the BSC. Anyway, out of 619 use surveys, 317 or 51% were what I call a la carte users that turn the cabinet on when they're using it and off when they leave. 302 users, or 49%, were in the something always on camp, and we'll call them the maintainers. So about half the people turn the cabinet off at the end of the day and half leave it on in some fashion. Of the maintainers, 40% would turn the cabinets off and leave the fans on. This is the light blue wedge on the right side pie. This is probably intended to maintain the cleanliness and containment of the BSC work area. 31% were to turn the BSC off but leave the UV light on. This is the purple wedge on the right side pie. This is probably intended to decontaminate the chamber. One of the factors influencing this is probably the age of the cabinets. People keep BSCs a long time, 50 to 25 years, sometimes even longer. Older cabinets that did not have timers for the UV. So if your procedure at the end of the day was to turn off the BSC, close the window, and turn on the UV, even if you realized you only need 1 to 3 hours of exposure, you wanted to go home. It was not uncommon to fall into a practice of just leaving the UV on when you were done with the BSC. I had mentioned earlier some of the new cabinets have a reduced flow standby mode, where you close the window and the fan goes to half speed or less. The traditional old style BSC with the permanent split capacitor AC motors couldn't reduce speed, and you couldn't run the fan at full speed with a closed window. So in the old days, your two choices for maintaining the BSC work area was either to turn off the cabinets and leave the fan running, or turn off the fan, close the window, and turn on the UV. And we found those two types comprise 71% of the maintainers, and there are two more types. 21% were operational almost always. This is the red wedge. Some of these may actually be 24-hour operations, like clinical laboratories in a busy hospital. I suspect most of these people are also intending to maintain the BSC work area and just didn't bother to turn anything off. And finally, 8% were kind of the belt and suspenders crowd that left both the fan and UV running. This is the light purple wedge with a blue outline. Addressing some of the reasons for maintaining can significantly reduce the resources consumed by BSCs. And there's a couple things we can do. Certainly, we can try education campaigns. Another approach would be to mitigate the additional consumption with some of the new features available on modern cabinets. Many new models from many manufacturers provide cabinets with a standby mode. In standby, the window is closed, the airflow is slow so that it maintains the clean area within the cabinet and containment in the cabinet, so you really shouldn't store anything in the cabinet overnight. But also the energy consumption is much less than standby, less than 100 watts for most of these units, and filter loading is also less. So kind of like our free exhaust approach, if we use education and standard procedures to encourage and support turning off cabinets when not using them, nights, weekends, and such, and we have standby capable cabinets, we could reduce the cost of operating BSCs in most organizations by over 50%, perhaps close to 80%. Well, what else could we do? In the old days, well, really now, but it's changing fast, we had limited information connectivity with BSCs. We would know when it was turned on or off. We could use that to open or close dampers, maybe turn on the remote exhaust fan. Sometimes we got a little silly and would connect the BSC alarm, so if your BSC alarm went off at the cabinet, it would also signal somewhere else, the building engineer's office or such. I say silly because it sounds good. If you want your freezer alarm to go off in a central office, why not the BSC? Well, there are very different kinds of equipment. A freezer operates without an operator, so if it stops working, we need to make sure someone knows. It might even stop working in the middle of the night. Alarm connectivity here makes perfect sense. A BSC has an operator, and alarms go off for various reasons. When you raise the window from closed to operating, the window position alarm goes off. When you close the window, that alarm goes off again. The operator knows what's going on because they're moving the window. The purpose for the alarm is so the operator knows if it moves accidentally or is in the wrong position. But does the facility engineer really need to know every time one of the 50 BSCs in the building is open or closed? Other connectivity will pull off fan speed, though I've not seen anyone have the data to use that to anticipate motor failure. And even if they could, BSC motors really don't fail that often. But times are changing and manufacturers are learning. New connectivity will have apps you can have on your phone to perhaps schedule usage, reserve the BSC for 10 a.m. on Thursday. New connectivity will sift through all the data and provide the facility engineer with just the bits they need, like exhaust air alarms. We can start noticing patterns like all the units on a particular exhaust trunk having problems. And thinking back to some of our previous discussions, laboratory energy consumption could be monitored. Overconsumption could be monitored and addressed. Efficiency could be rewarded and incentivized. What would you want to know from a connected BSC population? Let's imagine a super duper AI managed laboratory information system. Let's call it Igor. Igor can replace those sign-up sheets you find on some BSCs where people schedule their BSC times. If Igor knows what people are planning to do, the supplies they need, that Igor might be able to remind them if they forgot something. Igor could replace facilities in similar ways with modeling aggregate, could help facilities in similar ways with modeling aggregate use and suggesting allocation of equipment, service intervals, and so on. But let's think about us. What can Igor do for safety and sustainability? First, instructional and context-sensitive support information could be provided. If the system sees someone working in a BSC without surface decontamination, it could provide them with a short training presentation on proper setup. Metrics could be used in motivational ways. If the system somehow scored laboratories and even individuals on their protocol execution, it could we could reward high achievers and push those who need help. Third, there's a huge potential in assistance in regulatory compliance. In 2007, the Federal Demonstration Partnership in the U.S. estimated that 42% of American researchers' time is spent on administrative tasks versus 18% 20 years before. Regulatory compliance, a part of that administrative responsibility, is consuming more and more resources. In 2001, just 4% of the University of Pennsylvania's research budget went toward regulation compliance. Today, these activities account more than 20% of the budget. Significant portions of that responsibility falls on the safety office. How can a connected laboratory help us with that administrative burden? And the point there is, some of the things we need for sustainability and efficiency are, some of the resources we want are actually appealing to other groups within the laboratory that could be our partners in seeking these type of more advanced capabilities. So for sustainability, we see that after we do a couple of the obvious things, select the sustainable types of cabinets, minimizing external exhaust, select more sustainable models with standby modes and such, we run up against human behavior. Can connected BSCs, or how can connected BSCs help us promote more sustainable practices? My power company emails me these notices telling me how my energy consumption compares to my neighborhood average. We're incorporating social media into our selection of restaurants, home repair services, specific products. Why couldn't we explore ways to use connected BSCs and other laboratory equipment to bring visibility to sustainable behavior? We'd have to be very careful here, but if we modify we know we modify our behavior based on the people around us. If we see people bussing their own tables at a fast food place, we're more likely to clean up after ourselves. If people are speaking in muted tones in a laboratory, we're less likely to shout. And if you have some energy consuming B2 BSCs, you can see how much they are used. My message on BSC connectivity is for us to start thinking about that. The day will come when we can tap into this new environment, and it might be good to think about what would really help us in the laboratorians we support and what information might just be noise. Well, thanks for your time. That was my presentation, and now we get to my favorite part of hearing from you all, either now as a part of the presentation or afterwards. As you can see, my email is on the screen.
Thanks, Dave. There is definitely an opportunity for folks to submit additional questions in the question dialog box. Dave, I have a couple here for starters. One, the first question is, can you expand on your statement of having a quote-unquote free exhausted biosafety cabinet in a lab based on the lab being negatively pressurized? I'm not sure if I understood your statement. Lab ventilation is typically handled by the lab control system, which ensures the negatively pressurized space. It therefore ensures supply air is less than exhaust. So how does a single ducted exhaust from the biosafety cabinet not impact the total air exhausted from the room?
No, thank you for the opportunity to clarify. So if we have a laboratory room that is already drawing 300 CFM to maintain that negative pressure, their supply is 300 CFM extra. So their supply is 200 CFM, their exhaust is 300 CFM. That gives them the negative pressure that they need, and the automated building systems are designed to maintain that. And that's with no biosafety cabinets. If somebody wanted a biosafety cabinet, and in this case they weren't sure, but they just to be safe in their mind, they want to add, they want it to be externally exhausted. Exhausting a BSC in that room through that same system, which is allowed because that system is not recirculated, only would require an extra 60 CFM. So instead of drawing 300 CFM from the room, it would draw 360 CFM. We would probably have to bounce up the air supply to maintain that differential we want. But in that the cost of exhaust is most often in the money and resources spent into conditioning the supplied air. and heating the air that goes into the laboratory, humidifying or dehumidifying, propelling it there. If we already have to remove 300 CFM, and with the BSC we have to move 360, it's not that expensive. Now, if that same user said, well, I want I'm going to have two BSCs, and I don't want to have to decide, so I want both of them exhausted. That second one moved the exhaust from 360 to 720. So when I say free BSC, in a sense, the normal exhaust required from a negatively pressurized lab space is very close to that needed by one canopy connected A2. And so rather than putting everybody through what they would perceive as an excruciating inquisition as to their application and what chemicals, for some users, if they're willing to settle for just one exhausted cabinet, we wouldn't have that effort. And I think there needs to be more visibility on whether they really need it, but there's going to be some pushback if we start requiring it. So one way to ease that might be to say, well, as long as they don't want more than one, we're really not going to have an issue with that. I hope that helps some. But
I think that helps immensely, for sure. Thank you. There's another question here. In your experience, is there a quick list or an easy list of chemicals or volatiles that, if in use, then a biosafety a class 2 B2 would be essential, notwithstanding the risk assessment?
Well, no, there isn't. And personally, I think it's almost nothing. For me personally, the only time I will recommend a B2 without question is when it's required by regulation. And a lot of the regulations now for preparing hazardous drugs will actually specify a B2 cabinet. And in that case, if the law asks for a B2, you got to have a B2, even though there are technical arguments that it may not be necessary. Other than that, I'm trying to think if I've actually ever seen a true justification. Another class of use where I think there's good arguments for a B2. This might be changing in the future, but pharmaceutical research. I mean, if we think about the pharmaceutical R&D effort, what are they trying to do? They're trying to make more and more potent compounds. So smaller and smaller amounts will have huger and huger effects, and they're preparing them or working with them in a safety cabinet. In symboled A2, that powder is on the dirty side of the supply and exhaust filter and all inside the motor compartment, and is a real challenge to service and replace those components because you have the potential exposure to this powder, which we just talked about is actually, smart people are spending every day thinking about how to make it more and more powerful. If you put you move that application to a B2, the only place that powder goes is up inside the back wall to the exhaust filter. And then you could put in a bag in, bag out system. That's where you can remove and replace the exhaust filter while maintaining complete separation from the environment. And I think there's an argument to be made there that for that kind of preparation of pharmaceutical compounds, a B2, a bag in, bag out B2 has a lot of merit. But for me, those are the only two situations that I've really seen that seem to pass muster.
Okay, a question for you then is, in terms of facilities and design groups making wise, informed decisions with user groups and user teams for equipment selection, what would you see as kind of the ideal process for consultants and facility staff and scientific staff to work collaboratively to solve the equipment puzzle?
Sure. I think that if we were to try to require anybody who wanted an exhausted cabinet to provide the kind of detailed information that assessment required that we went through in the presentation, I think people would freak. I think you would have a lot of very smart, very angry people because they don't really have ready answers, and they've never had to answer that kind of question in detail before, and I think it would quickly become a disaster.
Right.
On the other hand, and this is my basic idea, if we were to say, no, it's only if you need more than one exhausted cabinet, or if you want a B2, that we need more information just to make sure we get you the right stuff. I could see. So my thought, and this is, I would really appreciate some feedback on this. I could see the design group saying oh yeah, so this is going to be our standard laboratory that people can build on or modify from. And then when they see this standard one, they say what they want as far as laboratory equipment, including the safety cabinet and fume hood. And those people that want more than that, more than one ventilated cabinet, either fume hood or canopied A2, well, they need to engage in a bigger discussion. I think at that point, you would only have that bigger discussion with a much smaller population, and because they are, in the best case, the most intensive users, they'll probably be ready to answer those questions. I mean, they're asking for all those ventilated cabinets because they use a boatload of volatile chemicals and need it. So that would be my thought, is that initial, I think there's some kind of the sense I've gotten in the past is when you all design large laboratory buildings, there's a process of working with users where you find the things they want and don't want. And I think that would be the group to start with, to see if this basic plus modification approach would work for most of the people in that building.
Right. Yeah, the concept of the 80-20 rule, that 80% of the challenges come from 20% of the users.
Yeah, exactly. Well, yeah, and if you push everybody through asking their chemicals, I mean, it's going to be perceived as incredibly onerous and painful. Mm-hmm. And so if you can bleed off, most of the people where it's not that big of a deal, and just focus on the ones that are really demanding of the resources, I think life becomes a lot easier for everyone.
Fair enough. There's one more question here. Do you feel that architects and designers and engineers perhaps treat these spaces as contained isolation rooms with Class 2 B2s versus an open lab? If that happens, perhaps we can fight the energy and operational cost challenges that we're faced with?
Could you ask that again? I mean, I understand there's an exciting tension between biosafety people that want to have contained laboratories.
Right.
So if anything gets out, it doesn't get out far.
Right.
And yet maybe the architect human engineering side, work flexibility side, that says, no, we want open areas. And I've sat in on a couple of presentations where they've talked about where they've had a laboratory acquired infection, and they talked about trying to figure out where it came from. And I think I remember one where it was an open lab environment, and I'm probably misremembering, but I kind of picture the safety officer going, and we couldn't figure out where they might have gotten it over here, they might have gotten it over there, because this guy worked everywhere because of the way the lab was designed. And gee, in the old days, they just would have been in this one room, and we could have known right away.
I guess,
does that make sense?
Yeah, I think that could be part of it. The question, I think, in general is if designers are focused on specialty use that would mandate, let's call it a ducted biosafety cabinet like a Class 2 B2, would it be simpler to have that in a dedicated, isolated space to make balancing the supply and exhaust of that space very specific and isolated, as opposed to trying to deal with ducted cabinets in more open work areas.
Absolutely, because one of the perennial tensions, and the people on the call may have run into this, is that the official recommendation for a B2 cabinet is that it be connected to a dedicated exhaust, defined as one VSC connected to one duct connected to one fan on the roof. And the exhaust management industry has all these incredibly sophisticated systems that allow you to have a varying demand and opening closing dampers and adjust for the fume hoods in use over here but not over there, and it moves all around, and they're always saying, oh, we can do B2s, and to date that has not really worked out that well in all cases, because B2s have such a large static pressure requirement and pull the balance of the room off so much. Having that kind of flexibility is tricky. So if you had a laboratory building, it seems to me, if you could put one or two B2s in the building or on a floor, and those rooms were managed so that they had the dedicated exhaust, and you had the ability to handle when the exhaust is turned on and turned off, which is a significant engineering challenge, I know. I think you would greatly simplify the challenge for the rest of the building. You would provide B2s for those people who need it, but yet the cost and sustainability of the entire building would be much more controlled. So I think there's a lot of potential there.
Interesting. Well, that really helps quite a lot. I think, Dave, that's the last question that we have for the day, and we're close to the top of the hour. So on behalf of SLCan, I just wanted to make sure that I said thank you very much. It's been a great presentation. And for those people who are on the line, David's email address is here on the screen, so make sure that you take that down and contact him with any additional questions or follow-up information that you'd like from David. David, thank you very much for your presentation today. It was great.
Oh, and thank you. Thank you all for the time. I appreciate it.
All right. Without further ado, we'll sign off. Have a great day.
Bye.
Bye-bye.